Good morning, everyone, and welcome. My name is Jennifer Nyman. I'm with Geosyntec Consultants. We are the coordinator of the webinar series on behalf of SERDP and ESTCP. This webinar is the second in a two-part series on managing AFFF impacts to subsurface environments and assessing PFAS-free foams. The first part of this series webinar was held 2 weeks ago and is available on the SERDP and ESTCP website. Today, we will have a brief overview of SERDP and ESTCP, followed by two technical presentations. First, Joe Quinnen of Arcadis and Terry Reed of Aqua Aerobic Systems will discuss sustainable, cost-effective groundwater treatment technologies for PFAS removal. Their presentation will be followed by a question and answer session. Then Dr. Tim Long of Arizona State University will talk about modular design strategies used to design novel formulations for PFAS-free firefighting foams. Tim's presentation will also be followed by a question and answer session. And we'll conclude the webinar with a question and answer session featuring all of today's speakers. The next few slides provide some instructions on optimizing your experience with the webinar. If you haven't done so already, you can download Zoom at the link shown here and provided to you in your webinar registration confirmation email. If you can't download Zoom, you might view the slides using a compatible internet browser like Firefox, IE, or Edge, and by creating a free Zoom account. If you're unable to view the slides or if your screen freezes, you can try keying Control plus F5 at the same time, and that performs a hard refresh. If you're accessing the audio through your computer and have any difficulties, click the arrow next to the Join Audio button and select Test Speaker and Microphone and follow the prompts as they appear on your screen. If you continue to experience any difficulties, please just call into the conference line shown here. You may also submit a comment about technical difficulties using the chat function at the bottom of your screen. Please use that chat box just for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. In case of any continued technical difficulties, you can always download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only. You may submit questions by using the Q&A box on your screen. You don't have to wait until the Q&A session to submit your questions, and in fact, we would encourage you to submit questions in advance of that session. When submitting your questions, please make sure to add your organizational name at the end of your question. And with that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program Area. Dr. Leeson has been with SERDP and ESTCP since 2001. Prior to that, she was a research leader at the Patel Memorial Institute, where she conducted research on in situ bioremediation and the design and implementation of biological, chemical, and physical treatment technologies. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thank you, Jennifer, and thanks to everyone who joined us today. I'm going to quickly move you along to our key presentations today, but before we do, I'd like to give you just a little bit of an overview of who we are in terms of SERDP and ESTCP. These are two companion programs, and we are the DoD's environmental technology programs, where SERDP is our research and development program in partnership with the Department of Energy and the Environmental Protection Agency. And ESTCP is our demonstration and validation program, where we take the research that comes out of SERDP or other research programs, and we take it to the field or at close to full scale so that we can really validate that, so that we can accelerate commercialization or broader adoption of the technologies that we're looking at. We have a couple of drivers for the sort of work we fund. First is we are looking at the sustainment of our testing and training ranges, our facilities and operations, and this, as you can imagine, is very broad. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munitions constituents, as well as still many other issues. And then we also are looking at reducing current and future liability. Part of that is pollution prevention, where we're looking at the elimination of different pollutants or hazardous materials and their different operations on our installations. And then, of course, we also are dealing with contamination from past practices. And this encompasses those chemicals in groundwater, soils, sediments. It also includes a UXO liability. And then we're also always looking to the future in terms of what are emerging chemicals of concern that are coming out. We have several main focus areas shown here. And what I'm really going to highlight today is some of our work on PFAS and AFFF, which will be the topic of the presentations today. Shown here is an overview of our entire PFAS and AFFF program, and I show it here really as a reference for you, and we will get the link to this website will be placed in the chat room in a second. And this is an interactive graphic that you'll find on our website, and above the date line shows all the different research areas that we've funded under SERDP. And each of those research areas typically represent more than one project. It's a body of projects that were funded under that particular topic area. If you click on the box, it will take you to a page that shows you a little more detail about what was the research question at that time, as well as the projects that were selected there. And then below the date line, you will see the ESTCP topics that were released. In this case, many of these are single projects. And then you can also see that some are groups of projects by year. And as we've progressed in our knowledge of PFAS, we have been funding more and more field efforts as well. So you'll see that in this graph. And so today we are focused on two different projects that came out of this program. It's a joint effort that will be looking at a project that's dealing with PFAS treatment, as well as a project that was dealing with development of PFAS-free aqueous film-forming foams. Our webinar series is really a key portion of our program here, and you'll see in upcoming that we have a number of different seminars coming up. And you can get to that by going to this link here that shows our entire webinar series. And very importantly, I also wanted to mention that if you go to this page, not only can you register for the upcoming webinars that I showed previously, but you can also get to the archived versions of previous webinars. So even if you missed the live version, you can go back and still see what we've done in the past. I also wanted to point out that coming up towards the end of this year will be the SERDP and ESTCP annual symposium. This is an excellent way to get a summary of what's being funded by SERDP and ESTCP. Every ongoing project we have will have either a platform or a poster presentation. So it's a great way to see some of the new work that's coming out. This symposium will be virtual this year due to the situation with COVID, and registration is now opened. So at this point, Jennifer, I'll turn it back to you.
Thank you. And it is now my pleasure to introduce our first two speakers. Joe Quinnen is a Senior Vice President with Arcadis in Novi, Michigan. He has more than 30 years of professional experience in environmental consulting, and he's a co-author of the book Remediation Hydraulics. Joe serves as a technical lead for Arcadis's PFAS programs for the Department of Defense and is the North American Director of Emerging Contaminants. He earned his bachelor's and his master's degrees in geological engineering from Michigan Technological University. Terry Reed is the Director of Research and Development for Aqua Aerobic Systems in Loves Park, Illinois. He oversees activities for product enhancement, new product design, and product development in the areas of biological treatment, filtration, and membrane technologies. He has authored numerous publications on nutrient removal, carbon diversion, membrane separation, and operational control strategies, and was a past recipient of the Water Environment Federation Innovative Technology Award. Tim earned his master's degree in product design and development from Northwestern University. Joe, I'll turn it over to you. Please proceed.
Thank you, Jennifer. So on slide 21, I'm going to talk about the introduction and the outline today. So we will cover briefly the background and objectives, the test design. We'll talk about the performance assessment that's completed initially at Horsham Air Guard Station and the cost assessment. And then we've also initiated a subsequent test at the Willow Grove Station. It's a neighboring facility with slightly different conditions. And finally, we'll wrap it up with a discussion on the benefits to the DoD. Slide 22, basically the background of the submicron activated powdered carbon and ceramic membrane filter. It's a technology that's driven by the increasing regulations of PFAS compounds and the broad spectrum of cost-effective treatment capability, parts per trillion level. That's really the big issue. So Aqua Aerobic System, Terry's team, has adapted this technology from drinking water technology deployed in Japan. And they've been using it on different contaminants for the last 10 years and treatment applications for up to 40 million gallons per day. So what they've actually done is taken this technology now and applied it toward PFAS treatment, and that's what we're going to discuss today. Slide 23 talks about our key performance objectives. Basically, we have three that we've met through our work at the Horsham Air Guard Station. We were looking at treatment, longevity, and selectivity. We want to be able to cost effectively treat PFAS and make sure we can not only treat PFOS and PFOA, but a broader spectra. So to measure that success criteria, we're looking at those two compounds as well as the 6 compounds in the UCM3 list and working to get below 70 nanograms per liter there. Because the SPAC system uses a reactor, we're trying to minimize the retentate washing for the spent SPAC and ultimately minimizing the waste there. And then the last objective, this ultimately is going to make the technology very cost competitive by minimizing the waste through the concentration of the spent SPAC. We can dramatically reduce the costs of waste management and disposal. So ultimately, we're able to super concentrate the SPAC after it's spent, and that's going to lead to very cost-effective application. So on slide 24, I will pass the baton to Terry.
Thank you, Joe, and good morning, everybody. The results we're going to be presenting today reflect testing that was conducted over a 12-month period starting July of 2020. The technology centers around a carbon-based sorbent material that we identify as Aqua PR206. It's a superfine colloidal suspension that's managed in a slurry form. It's been generically termed as superfine powdered activated carbon, or SPAC, but in this case, it's been specifically formulated for the application that we're about to discuss, and you'll see some differences between how it may have been used in water treatment versus what we're doing with perfluorinated compounds. The general process flow of the technology we'll be discussing is depicted on the right. Items 1 and 2 on the left-hand side are pre-treatment units. One is a strainer and one is a cloth media filter. That's in cases where we're drawing water that may have elevated levels of sediment or other suspended matter. Otherwise, if we're pulling out of a groundwater that's fairly clean, pump 3 will actually take the untreated water and pump it to item 4, the sorbent reactor. That reactor maintains a suspension of this Aqua PR206 sorbent material anywhere from maybe 1 gram per liter up to 80 grams per liter. That's where the contact is happening and the PFAS is being absorbed. The slurry is then pumped to a separator and recirculated back into the absorption reactor. And while that's occurring, we are pulling filtrate out of the system through a 0.1 micron barrier. And so this 0.1 micron barrier is rejecting all the sorbent material as well as the PFAS that's tied with it and producing a high quality effluent that is suitable for discharge at that point. We do incorporate a small holding tank to store a few minutes of filtrate that we will use for back pulsing the separator on a maybe hourly basis And what that's doing is reversing the flow path across the separator and dislodging any surface material off the surface of the separator. And then that material gets swept away by the cross flow and brought back into the absorption reactor for treatment. So that's pretty much the process flow of the mainstream of the system from introduction to discharge. The units that you see here on the lower portion of the screen, 9, 10, and 11, are used for concentrating the sorbent before disposal. So we have a unit here, 9, which concentrates the sorbent material. The water is then, that's taken out of that, is pumped back into the system for treatment. Meanwhile, the thickened sorbent is stored, and then at some point, ultimately disposed of as depicted here with item 11. Over the 12-month period, we performed over 26 different tests, and we looked at some of the key performance indicators or variables that would influence PFAS removal, including the hydraulic loading rate to the system. Detention time was a critical factor, the sorbent concentration, and that's where we differ a little bit, because we're looking at anywhere from 0.5 to 100 grams per liter, not milligrams per liter. So this is a significantly concentrated material that we're maintaining in that reactor. Up front, we considered pre-treatment and its impact on performance. We also looked at mixing energy and methods of improving performance, and then finally the back pulse interval and how we can maintain reliability with the separation system. When we got on site for the first time, we were a bit surprised to see the variation in the water quality. Normally, this outfall is pretty clear and somewhere in the 1 to 2 NTU range, but as you can see in this photo here, it doesn't take much in terms of rainfall events or wind to disrupt the sediment and change the characteristics to being very turbid in a short amount of time. In fact, from test 10, you see here that we went from about 1 NTU to nearly 100 NTU, or a couple hundred milligrams per liter suspended solids in just minutes or hours. And so we had to look at, in the case of the surface water, putting a pretreatment system in. And fortunately, we had a small cloth media filter, which is depicted in this lower graphic here, which is used primarily just to remove the sediment so that we could then focus on PFAS removal of the filtered water. We did evaluate the PFAS removal across this system, and pre-treatment really had no impact on PFAS. So it was really an opportunity for us to optimize the performance of the downstream system. One thing to keep in mind is that because of this very tight separator at the end of the process, despite what's happening to the influent conditions, the effluent is pretty high quality in terms of final effluent, somewhere in the 0.05 NTU range. And so we took this 26 tests and we grouped them into 3 different conditions. And we'll start with test condition A, which is a single pass operation. We're moderately high on the hydraulic loading rate, but more importantly, we focused on a short detention time, in this case of 5 minutes, and a moderate concentration of sorbent of 40 grams per liter. Moderate being something that could be as high as 100 grams per liter. This is the characteristics of the feed water over that test period. The total PFAS was about 8,000 parts per trillion, predominantly made of PFAS. And so from a metric standpoint, we had to identify what we were trying to achieve. And these graphs are going to be very similar. On the y-axis, we have the concentration of the PFAS. In this particular case, it's the sum of PFOS and PFOA. Secondary y-axis is percent removal, also depicted by this red line. More importantly, on this x-axis is the loading capacity of the system. And we put it in terms of the sum of PFOA and PFOS in terms of micrograms of pollutant per gram of sorbent. So the more we go to the right end of this graphic, the more we've loaded the sorbent material. And as you can see, individual sampling of the influent showed combined PFOA and PFOS of nearly 5,000 parts per trillion. And the effluent, on the other hand, was below limits of quantification for the bulk of the study. We did have 2 metric points throughout our testing, the first being this black dashed line, which is indicating 70 part per trillion level of combined PFOA, PFOS. And then the next one is a 10% breakthrough that we would allow us to compare to literature data in terms of the combined PFOA and PFOS. And what's interesting is that we were actually able to load the sorbent to about 260 micrograms of pollutant per gram of sorbent before we actually reached the 70 part per trillion combined PFOA, PFOS. Now, in comparison, and putting this in context, what we would have expected for granular activated carbon would have been down in this 6 to 10 microgram per gram range. So we indeed were seeing significantly higher absorption rates in this testing. But more importantly, as Joe mentioned, we were looking at a broad spectrum removal of larger components in smaller chain compounds like PFBS and PFHXS. And so we identified the UCM3 compounds, those 6 compounds, as a good surrogate to identify how well the system was doing. In this test condition A, the concentration was somewhere between 3 and 10,000 parts per trillion, but averaged about 6,000. And again, we were at very low levels throughout the testing, not reaching 70 parts per trillion of combined UCM3 until about 160 micrograms per gram. Meanwhile, if we looked at 10% removal, that was closer to double that value, which shows us that we're not seeing a rapid drop-off in performance after we've reached a certain endpoint. So it's kind of a subtle change. So test condition B, we did some changes. We looked at a longer detention time, but a lower sorbent level. And in this testing, we had slightly more stable feed quality conditions, but a little bit stronger at nearly 11,000 parts per trillion. And again, looking at the combined PFOA and PFOS, in this case, the concentration was pretty stable at about 6,000 parts per trillion. And as a result, most of the samples were below the limits of quantification, up to 400 micrograms of combined PFOA, PFOS per gram of sorbent, where we hit the 70 part per trillion level. And unfortunately or fortunately, we terminated the test a little bit too early because we didn't see the 10% breakthrough point on the combined PFOA and PFOS. But more importantly, we were interested in how this system worked with the UCM3 compounds. And again, the combined concentration was fairly stable at around 7,000 or 8,000 parts per trillion, with most of the samples below the limit of quantification up to about 160, 170 micrograms per gram. And again, this is combined, the sum of all combined compounds, not just each one individually. But when we looked at the 10% breakthrough, that was nearly 600 micrograms per gram. So that was very interesting from a treatment standpoint. So test condition 3, during the final portion of the study, we ran a series of tests in a different configuration. It was in series, where we used 2 units, both with a short detention time of 5 and 7.5 minutes at moderate concentration of sorbent. And the objective of this testing wasn't necessarily to demonstrate high absorption rates, but to replicate practical application in the field, where we'd run 7 days. And rather than waiting months to get to exhaustion, we would operate for 7 days and replace a little bit of the sorbent material. And at the end of that 7 days, because it's a slurry, it allowed us to do some things with concentrating. So we would take the system, run it continuously for 7 days, and at the end of the 7 days, we would take the system offline for about half an hour, where we would concentrate the sorbent, remove it, and then replace it, and then put the system back online. And in terms of performance in this operation over the 7 days, this graph is pretty much the same as we saw before, except we're looking at the 7-day operation. The UCM3 compounds were about 5,000 parts per trillion and below limits of quantification. Throughout most of that testing, we started to measure some towards the end of that 7-day period, but getting nearly 100% removal over that time period. And so that was interesting from a performance standpoint. However, we wanted to compare, as Joe mentioned, part of the program was to evaluate the economic considerations of the technology. And what you see in this upper graphic is where we used the data that we gathered from this testing at the Horsham Air Guard Station, and then we ran a rapid small-scale column test on granular activated carbon on the same water. And you'll note this is on a log scale, because if we used a regular scale, we wouldn't see the GAC absorbent rate. And as a result, what you see is that the absorption capacity of the superfine powdered activated carbon is orders of magnitude higher than what we saw for GAC. And this pretty much mirrored what we saw in the literature in that range of 2 to 3 micrograms per gram based on this particular water quality, where we were upwards of 2 to 300. And this is based on 10% breakthrough point. So what is the ratio of the two? If the two of the aqua PR 206 absorbent material and the granule activated carbon were equal, that ratio would be 1. So we looked at each of the 6 UCMR3 compounds and took the ratio of the absorbent capacity, and what you can see is that most of the compounds were at or above about 100 times increased performance capacity with this superfine absorbent material. In fact, the sum of all the compounds was close to 300 times greater than what we saw with the granule activated carbon. There's one compound missing, that's PFNA, that was not actually measured in the influence, so we didn't include it in the graphic. A big part of the performance as well is waste minimization. Now, this technology has a head start because the absorbent capacity being a couple hundred times greater than what we see for GAC, we're going to start with a much smaller amount of absorbent material. But as we operate the system, we're going to maintain a certain concentration in the reactor. That's not what we're actually going to dispose of at the end of the week. What we're going to do at the end of the week is go through some thickening to the extent where what we're actually disposing is about 5% of the volume that we're maintaining in the absorbent reactor. So in other words, we're really trying to limit the volume and the mass of what we're disposing from the system, and that plays into the economic considerations pretty heavily. Before, in the proposal stage to the ESTCP, we put together what we felt were the benefits to the DoD with regards to the technology. We looked at the capital expenditures of what we expected for this superfine powder activated carbon system versus what we would expect for the granule activated carbon. And of course, we had increased capital cost by a factor of 2 to 3, but we felt that the savings in operation and maintenance would pay for that difference in capital costs in a short amount of time. And in fact, in the evaluation of a 20-year life cycle cost, the payback period was about 3 to 4 years with this technology. That was on a fictitious waste based upon some estimated absorbent ratios. So really, our goal was to, over that 12-month period, take the actual data that we've compiled and compare it to the actual data that we gathered for granule activated carbon, and using the Horsham data, repeat that economic analysis. And when we look over at the capital costs, not much change there. Our system is still a little bit more expensive from a capital standpoint, but a couple things happened in the operation expenditures. First off, our absorbent material performed a little better than what we proposed, and then the granule activated carbon, I think in our proposal stage, we gave it a little bit too high of absorption rate. So this difference grew, resulting in a significantly reduced operation cost that produced a payback period of somewhere in the 3 to 5 months as opposed to 3 to 5 years. And again, this is based on the data that we've been gathering over the last year. As Joe mentioned, towards the end of the study, we had an opportunity to redeploy the system to the nearby Willow Grove Naval Air Station, where we could then see how well the technology performed on groundwater as opposed to surface water. And one of the main objectives was for us to recognize that we're using the same production level absorbent, the same production level separator, and the same process flow diagram. And what that would allow us to do in the lab on a short-term basis, we could have an accurate predictor of what to expect in the field. So before we got on site, we actually received some water sample from Horsham or from Willow Grove and performed this testing on the lab. And what we found is that the combined PFOA and PFOS was about 37,000 parts per trillion, and we were able to knock it down below the limit of quantification for the most part, up to about 1,200 micrograms per gram. That was 3 to 4 times higher than what we saw in the surface water. And so now the next step is to put units on site and see if that came true. And so we set up the first two tests in a similar fashion to what we did at the Horsham facility, moderate hydraulic loading rate. And we used 2 units, one with 10 minutes detention and 20 grams per liter, and one with 20 minutes detention and 10 grams per liter. So same mass, just different detention times. This is the makeup of the water that we saw during the testing with total PFAS levels of 40,000 parts per trillion, predominantly PFOS. The results indicated that the lab scale study matched the field pilot pretty closely. If we look down to this table at the bottom, where we have the 3 tests, we've got the lab, test 1A and test 1B. In terms of PFAS, looking at the influent versus effluent, all the 3 tests worked out quite well. We saw very close, nearly identical adsorbent rates for test 1A and 1B, which indicated that the adsorption is fairly rapid and detention times between 10 and 20 minutes really didn't have much of an impact. Now, we did see the lab was slightly lower on the adsorption rate here. That's only because we ran out of water. We actually never saw any samples go above the limit of quantification. I suspect that had we had more sample, this would have been closer to the 1600 mark. PFOA, a little more difficult to remove, but at much lower concentrations. We had a similar story between 3,000 and 3,400 parts per trillion, down to less than 70, at adsorption rates of 170 to 200 micrograms per gram. And again, these were 4 to 5 times higher than what we're seeing in the surface water. So in conclusion, the Aqua PR206 superfine powder activated carbon is superior to granular activated carbon. It's orders of magnitude more absorbent than what we would see with GAC. More importantly, in terms of what benefits it offers to, in this case, the Department of Defense, it offers significantly lower disposal and replacement costs where the operation expenditures are less than 10% of what we'd see with granular activated carbon. But some other side benefits is that it's an automated process that we ran by and large remotely. And in terms of absorbent replacement, we were able to do that in less than an hour and closer to maybe 30 minutes. Because it's a slurry, it allows us to use pumps, valves, and tanks and controls to replace the absorbent material automatically. And then a side benefit as well is because we're using that robust separator with a 0.1 micron barrier, that the effluent quality coming out of that is quite good. So that concludes the presentation. I'd like to acknowledge a few people, some of our co-PIs on the project, Jeff McDonough from Arcadis and Chris Bologna from the Colorado School of Mines, who are key players in this overall study. But also from the site perspective, we really have to give thanks to, at the Horsham Air Guard Station, Keith Freihofer and Lee DePerzia and their team, as well as Jason Spiker and his team at the Willow Grove facility. So that concludes my presentation, and I'll turn it over for questions. Thank you.
Thank you very much, Terry and Joe. I want to take this opportunity to remind our audience that at this point you can submit questions using the Q&A box through the Zoom software. And we have received a number of questions. So first, Terry, you showed a large range in potential sorbent concentrations. What influences that concentration that's necessary? Is it the known PFAS influent concentration or other competing contaminants or anything else?
Yeah, that's a good question. In terms of the concentration, it's really dependent upon the mass absorbent that we maintain in the system. So the actual concentration will do a couple things. It will affect our detention time that we make, size the system for, and then the absorbent replacement interval. Initially, we started off with really high concentrations and longer detention times to extend that replacement interval. But what we found is that what that does is it just subjects the absorbent material, whether it's ours or other materials, to longer runs and exposure to scaling and biofouling. So our thought was, let's use a lower concentration and shorter and moderate detention times, and try to get the replacement interval within a short, 1 or 2 week period that can be done automated. So there's but to your point, the absorbent concentration will also be affected based upon the strength of the waste and the co-contaminants coming in as well. And it's part of the compiled data that we're putting together.
Okay. And can you just elaborate on how a high dissolved organic carbon concentration might affect the efficacy of the process?
Yeah, also a good question. It's something that we focused on quite a lot. And this whole testing was predated by some testing we've done where we looked at co-contaminants like DOC, NOM, and BTEX and other compounds. And there definitely is, depending on the component, some impact on PFAS removal. That's something that we, require to test on every individual site, which is why it was important for us to develop a quick lab scale study that would allow us to do this accurate predictive measurement. So, each waste is unique. And in Horsham, for example, we saw the TOC normally between 2 and 4 milligrams per liter, but during those spikes, it really shot up. Whereas on the groundwater, it was fairly low at, I think, about 1 to 2 milligrams per liter.
Okay, thank you. This next question is from the state of Michigan. And the question is whether you've considered or compared this process to a similar process, but using resin instead, which would allow for stripping of the PFAS off of the resin.
That is part of the ongoing study. Most of what we've been doing is direct comparisons with granular activated carbon, but also trying to take information of other studies we've seen with ion exchange and draw those comparisons. I don't know, Joe, is that something you would mind commenting on?
Yes, Jerry, that is a great question. So the reason we decided, or we recommended doing the test at the Willow Grove Naval Air Station is because Colorado School of Mines, Tim Strathman, had done a pretty extensive evaluation of resin. So what we wanted to do is be able to compare it to that performance database that Tim's compiled, looking at a pretty wide range of resins. So now we'll be able to extend our cost comparison not only to GAC, but we'll be able to look at how it did compared to resin and see what that sweet spot is.
Wonderful, thank you. Next, we've received a number of questions about disposing of SPAC waste. Have you explored different options? How would it be disposed?
Yeah, that's definitely a point of interest for us as well with regards to the material. What we've been looking at is similar disposal methods to what you might do with a single-use resin or granular activated carbon. One thing that's a little bit different, one thing that's largely different is the amount of sorbent that we're actually using is a lot less. So that helps in terms of improving the disposal costs and hauling costs if you're, for example, incinerating it. But because it's a slurry with some BTU value, we actually have opportunities to look at destructive technologies that may not be as readily available with other sorbent type materials. So that's definitely an area of interest that we will continue to be looking into. Joe, do you have any comments on that?
Oh, I think you hit the hot spots there, Terry.
Okay, thanks.
And maybe for this question, we'll start with Joe. Do you have any information about whether existing GAC treatment systems that are fairly widespread can be somehow converted for use with the superfine activated carbon?
Well, that's a great question. When we first started doing the work, lots of practitioners had limited experience with SPAC, and everybody thought it was too complicated to be cost effective. The great thing about what Terry and his team at Aqua Aerobics have done, they've applied lessons learned from almost a decade in water treatment and really optimized the system. So, yep, the membrane is a bit more expensive in terms of CapEx. The system's automated. So ultimately, it translates into significantly reduced operational expenses, and it's a lot simpler to run than some of these GAC systems are. So I think the big obstacle, as much as demonstrating technical efficacy, which I think we're working through now, is demonstrating to folks that this actually is really pretty easy to do, and it is a viable commercial technology today.
Thank you, Joe. Anything to add, Terry?
No, I think that was a good explanation. Thank you.
All right. And did you look at absorption of PFAS to the walls of the reactors or to the equipment of the treatment system? And how did you account for that, if so?
We did. That's really an interesting question. We did some work early on to quantify the PFAS reduction without the sorbent material. One question was how much PFAS would absorb to the separator system. We thought there might be some. We were hopeful there would be some, but proved not to be. And then similar with regards to the walls. There may be some accumulation of PFAS on the walls, but in terms of performance, it doesn't affect it. One thing that we've done to clean out the system, which appeared to be pretty effective, is that in between runs, what we would do is take a small amount of the sorbent material and recirculate it. And the scouring effect of this material across it has I think a Mohs hardness of 2 to 3, and therefore it would have a scouring effect on the walls of the piping and equipment. And it actually allowed us then to purge any sort of the PFAS out of the system so that we could get a clean run on the next go around. So I don't think there's a significant amount, but it's something that we've addressed through using the sorbent for cleaning purposes.
All right, thank you. And we have time for just a couple more questions. And for longer operational periods, will biological growth in the system be an issue? And if so, is there a way it can be controlled?
Yeah, absolutely. That's something that we've seen in other technologies, and when we first started developing it, we thought, let's see how long we can go before we need to replace the material, because that was kind of the prevailing thought, is that the longer you could go, the better. And all that really does is expose the material to subjects it to scaling potential as well as biofouling. So our response to that is actually to, rather than waiting, say, 3 months or 6 months to replace the material, let's do it a little bit on a weekly basis, which ensures that we always have a fresh supply of this sorbent material. So if there is a chance for any sort of biofouling to occur, that we're replacing that on a frequent basis. So the replacement interval is really the tool that allows us to prevent that biofouling from occurring.
Great. And one last question. Did you fit any isotherms to the data? Did you create like sorption isotherms? Do you have enough data for that yet?
So we did some of that work early on in the lab, as far as tying that to the performance of the over the last 12 months at Horsham. We haven't. I don't know, Joe. Is that something that Chris had looked at, or is that something? I don't think that we had.
That's a good question. We haven't looked at it yet, and one of the big issues when we talk about comparing SPAC to resin to GAC is there's usually a different way of looking at it. So ultimately, the specific sorbents is a really good way to compare performance for SPAC, but the one that's uniform for comparison is cost. So I think we'll undoubtedly look at things like the isotherm to better understand performance and use that to develop modular approaches to be able to streamline application. The big advantage of the approach right now with the SPAC CMF is Terry does have this small system that he can do bench scale, and they're pretty close to field scale. So ultimately, some of the design approaches we're taking are intended to circumvent some of the challenges that you see with resin or that you might see with GAC. So it may not be as critical to have an isotherm as you might think, but I think we'll be looking at that in our final evaluation.
Got it. Thank you very much, Joe, and thanks, Terry. With that, we'll move on to the second technical presentation. Terry and Joe will come back online at the end of the webinar for some additional questions that we have. Our second speaker today is Dr. Tim Long, who is a faculty member at Arizona State University with appointments in both the School of Molecular Sciences and the School of Engineering, Matter, Transport, and Energy. Tim also serves as the director of the ASU Biodesign Center for Sustainable Macromolecular Materials and Manufacturing. His interdisciplinary research group establishes fundamental relationships of macromolecular structure with physical properties and advanced processing with a goal of more sustainable chemistry and engineering. Tim has published over 375 peer-reviewed publications and book chapters. He received his doctoral degree in chemistry from Virginia Tech. Tim, please proceed.
Okay, thank you, Jennifer, and I'm assuming you can hear me okay. So let's go ahead and get started. Well, you know, it's a pleasure to follow Joe and Terry, and I think this lecture really deals with, you know, how do we make their life easier? Like, how do we at the get-go, right, remove PFAS, right, from a waste stream? How do we eliminate that, and how do we design next generation materials, right, to do just that? So that's my challenge, and that's what I want to describe to you in my time with you today. And hopefully you'll see some of our strategy, you know, some of our vision, you know, how we approach things, what's our challenges. Oops. So first thing I'll do is I'll give a quick background in terms of, you know, why do we decide this pathway? You know, there's many different ways to eliminate those surfactants, those small molecules. What was the thinking, you know, from our laboratories? You know, what were we going to do? How are we going to design these differently? And then look at their properties and their performance. You know, basically, what motivated us and what were our objectives? What could we bring to the table? So I'll also show you some results of those polymers that we designed, and we'll look at, in partnership with others, the fire evaluation. How do they perform? How do we scale the polymer up, and how does it actually, you know, put out a fire, right? So that's really the key metric, right? At the end of the day, that's where the rubber meets the road. And we also want to look at, you know, some other synergistic design parameters. You know, what strategies can we take? What are some universal ways, right, to think about the design of some next generation, you know, fire suppression foams? So I'll conclude, and then I'll describe some of the benefits to the DoD. So the first strategy that we chose was a polymer one, right? And again, as Jennifer mentioned, I'm a director of a polymer center here at Arizona State. You know, so our first thinking is that, wow, polymers can solve this problem, right? And the polymers that we choose actually were based on some kind of, you know, earlier research, and we chose a fully aromatic polymer. For people who aren't chemists, in the yellow box, right, these are polymers that only contain, right, these aromatic rings. Right, in this case, this is a polyimide, and polyimides are really well known in commerce and commercial applications. You know, the DoD, NASA, others, right, have used, you know, polyimides for a variety of high performance applications, right? Aerospace, automotive, medical, electronics. You know, why are all these applications taking advantage of polyimides? Well, it's this fully aromatic character, right? It's all these, you know, kind of benzene rings that comprise the main chain of this polymer. These polymers are also recognized to being flame resistant, right? Fire resistant, right? Why is that? Well, they're fully aromatic, right? So they're not going to burn like octane, for example, right? So these fully aromatic polymers are recognized, right, for their resistance, right, to fire. They're flame retardant inherently in their chemical structure. They're also resistant to chemicals, right? These molecules tend to be completely insoluble in organic solvents. And in addition to this resistance, right, they're also mechanically robust, right, and they have exceptionally high temperature, you know, stability, some of the highest temperature stabilities that are known, right, in the polymer field. So we're going to talk a little bit about the polyimide kind of design space and why we chose them, and what are some of the potential, you know, advantages of a polymeric foam. So the objectives for my lecture are first to show you how do we make a polymeric surfactant? You know, what do we need to do? Like, what are the considerations from the chemistry standpoint or from a scale-up process, right, at a commercial scale, right? And we're going to be looking at fully aromatic or all aromatic polyimides. And I'll show you a little bit more of that structure again, and not to kind of, you know, drill down too deeply in the chemistry, but to kind of give you a sense of, why we're choosing these, and maybe some of these approaches can be extended to other systems. We also want to demonstrate an idea of cross-linking. As we suppress a fire, right, one of the major challenges, of course, is to not let any fire foam suppression agent, right, to migrate, to move into that waterway that we just looked at, right? How do we do that? Well, polymeric structures are going to be less diffusing, and polymeric structures have high molecular weight by definition. So we're going to talk about even cross-linking, or during the fire itself, using the fire to induce even a higher molecular weight or a less propensity to migrate. And we're also going to explore various pendant sulfonates. We're going to look at the sulfonate group, and sulfonates, as we'll see, are widely used in surfactants, right? That's the S, right, that we're all very comfortable with. But how we place those onto a polymer structure in order to impart foamability and tailor that fire performance, right? That's really the challenge of some of the efforts together with SERDP. So let's start out just briefly and go into polyimides. And again, this all aromatic structure, which you see on the lower left, that structure down there is known as Kapton, right? So if you're familiar with DuPont, there's Kapton. There's also other companies in the United States. Sabic, for example, has a product called Ultem. And what categorizes these polymers on the lower left, right, this all aromatic polyimide, right, is this inability to burn, right, and the very high temperature properties. Now, these properties are fantastic, but they're not going to form a foam, right? They're not going to be dispersible in water, right, form a foam in water. So we immediately have to take this idea of a high performance polymer that forms incredible char upon burning, right, and no migration. How do we render that polymer soluble or dispersible or foamable, right, in an aqueous medium? So typically the way we're going to do that is we're going to introduce these sulfonate groups, right? This is the S, the 3 O's, the minus and the plus with the sodium right next door, right? This is the sulfonate group, and by definition, those are going to impart hydrophilicity or dispersibility, right, in a water system, which is what we're looking for, right, if we want to dispense a foam, right, to suppress a fire. The other important feature for polyimides is the fact that they form high char yields. What's a char? Well, after we heat that up, do the molecules all vaporize upon heating, or do they essentially form a high molecular weight carbonaceous char that also serves to help suppress the fire or to suppress any type of oxygen ingress, right, into that system? So highly aromatic polymers have been widely used in aerospace applications, automotive applications, for these very reasons. But they have not seen use, right, in the suppression, right, of fire and foams. So let's get into a little bit of that, kind of technology together. So the first thing to do is to leverage a commercial process, right? Even though SERDP is dedicated to fundamental science and engineering, looking for fundamentally new solutions, right, we still want to have a lens, right, of commercial impact or commercial viability, right? So the first thing we did was to demonstrate that these polyamic acids, or this PAA, right, can be easily synthesized at room temperature. Why is this important? Well, we want to make these molecules in a commercially viable way, not using a lot of energy, and we'd like them to be affordable. So we can use this sulfonated diamine, this blue molecule on the upper right, and we can react it very classically with all the molecules that companies like DuPont and Sabic use routinely. And this polyamic acid, or PAA, that forms, right, is easily formed at room temperature. And then what we need to do, and what DuPont and Sabic do, is they imidize this structure at very high temperatures. Now, at first glance, you're going to say, wow, that doesn't seem very feasible, right? We're heating to 400 degrees C. That can't be a commercially viable process. Well, it is. Right, there's many products based on that approach, but we're going to remove that constraint a little bit later in the lecture and kind of show that now we can look at materials that are much easily manufactured more readily at scale. So these products down here on the lower right labeled polyimide, or PI, are water dispersible polymers. Of course, that depends, right, on the amount of that blue molecule, right, that sulfonate group. The more we put in, right, the more soluble that polymer becomes. So the main message for this particular kind of onset of our strategy was, yeah, let's take advantage of fully aromatic polyimides, but let's also take advantage of existing infrastructure commercially in the United States. Let's take advantage of reactors that exist and processes that exist so that we can actually translate this technology into a commercial product and one, right, that the DoD and other agencies can use. So first things first, we're going to do a simple experiment. We're going to take these sulfonated polyimides and we're going to look at their thermogravimetric analysis, right, a very common technique used in polymer science. Weight remaining versus temperature. And you'll see on that upper right plot, right, that all these polymers are going to be stable well over 400 degrees C. All right, that's good. The other thing we want to recognize is back to that word char, right? These high char yields, right? You look at the left axis here, the y-axis, right? You're looking at above 65% char. So when these molecules exceed the extreme temperatures, they immediately turn to carbon. And that carbon could have many advantages. As we just heard, it could actually serve to scavenge things. It can serve to suppress oxygen ingress. It can serve to suppress hydrocarbon fuel from migration across that interface. So lots of reasons why we chose that char yield. We also like the char because we don't want small molecules coming out of the foam, right? So we prefer, right, as we see high temperatures in the foam, that these molecules are essentially tied into a carbonaceous, basically product, right, at the end of the day, and they're not vaporizing into the air and potentially, harming people that are around that fire scene. The other thing we'll notice too is that despite the introduction of that sulfonate group, that blue molecule right here on the lower right, as I put more of it in, we see this decomposition temperature, right? The stability of the molecule is still in excess of 455 degrees C. So we're not compromising the thermal stability of these polymers despite introducing hydrophilicity and dispersibility into an aqueous media. So that's a really good, promising result for us. So let's go ahead and make some foams, right? At the end of the day, right, this is what SERDP is challenging me and many others, right, across the nation, right, to try to do. And in this particular case, we can take these polyimides, again, shown down here on the lower right. Hopefully you're seeing a little bit of chemistry today, not too much. But this image structure with these sulfonate groups, and we place that in water, and that you'll see in this kind of left image on the lower left, right, it forms a dark solution. While polyimides are typically not colorless, they are typically colored, and there's a lot of chemical reasons for that we could discuss, but that doesn't form a foam. Now, in the middle image, we can put a surfactant in something like sodium dodecyl sulfate, right, a classic surfactant. There's that sulfonate group again, right, so we're kind of borrowing from that SDS, kind of structure. And when we put SDS in water, yeah, sure, and lo and behold, yeah, it forms a beautiful foam, right? You see it in the middle. When we combine the surfactant, this SDS, with the polyimide that's sulfonated, lo and behold, for the first time, we also form foams, right? So this is quite encouraging. In fact, this foam on this right, we're chemists in the laboratory, actually making a foam for the first time with these polymers. It's kind of a new thing for us, right? But these form very nice foams at the concentrations that are typically used in firefighting, and we'll talk about that in a moment. But these foams are stable. We can look at them. They can sit on the bench top, and they form quite readily. So that's a really good metric for success, right, in this initial screening kind of exercise. We can also spend a lot of time looking at the foam, and I don't think a lot of people are doing this. This is an area that SERDP has been encouraging, is to fundamentally understand, what is the foam, and how does the foam microstructure influence, right, fire suppression? Lots of really critical fundamental questions, right, in that space. So in these scanning electron microscope images, right, these two images, you can see at 3% of the sulfonated polyimide or 6% of the sulfonated polyimide, and a little bit of that SDS down at about less than 0.2% by weight, right? These form very stable foams, and that bubble size, which I think is critical, and we're going to learn more about that in the future, I think, to suppressing foams, that bubble size can be controlled. And we can control it, as you can imagine, by, well, how much polymer do you place in the aqueous solution? Right? Obviously, the more polymer you have, you're going to get more foam, right? The density is going to be increased, and the viscosity might be increased because polymers inherently, right, are making things more viscous, right, due to their size. And also what we showed is that at the 3% and 6% levels, which is very typical for an AFFF, kind of solution, right, a concentration in water, these will form foams. So we don't need to use more. We probably could use less, but at this early, kind of research, we want to demonstrate at least that we're meeting the benchmarks right, of current products. So let's test the foam. What's the biggest challenge in that? Making enough of that polymer to test. So in collaboration with Jensen Hughes, fortunately, Brian Latimer at Virginia Tech, great colleague and a former employee at Jensen Hughes, is on our team. But we can take a scaled up production, right, of these sulfonated polyimides, right, and we can spray them onto this vertical kind of substrate, right, and we can look at expansion ratio, drainage time, and what we discovered was that, using this mil-spec nozzle and these mil-spec specifications, we could reach them, right? We're in the right ballpark. The biggest challenge here for synthetic chemists or people working in the laboratory is making it at scale, right? And again, why did we go with those commercial processes? We did that to make these at scale because we knew down the road we can't make milligrams of a product. We need to make hundreds of grams of a product, right? Which is something critical if we're going to translate this technology out of the lab. But you'll see the maximum drainage time right down that vertical substrate. You'll see the expansion ratio greater than 5, right? Those are the specifications, and you see that we're kind of in the ballpark, right? We're getting performance, that encourages us, right, to move forward on that. We also needed to do some preliminary ecotoxicology. I'm following Joe and Terry, which is always a dangerous thing because they know much more about this than I do. Right, but looking at the LC50, looking at the percent survival, right, the species, right, of this particular insect, for example, as a function of concentration. And using an SDS control, which is in green, you can see, yeah, the survival is going to decrease as the concentration gets higher. Well, how does the polymer compare? Let's just take the polymer. And in this particular preliminary data, it shows that that survival rate or that species, right, is longer, right, at higher concentrations. So that's a really encouraging thing. In fact, we did not go deeply into ecotoxicology, but we wanted to be able to at least quickly address the fact that we're not making a solution that could be worse than what we're trying to solve, right? We want to make sure that we're on the right pathway, and these are practically non-toxic, right, over the regime, right, that we've been interested in, kind of been guided by. So how do we go farther in the last 7 minutes or so? We're gonna take this idea and make it even easier. And how do we do that? Well, let's eliminate, right, that reaction at 400 degrees C. Okay, DuPont, help us out and make this molecule, but let's do it all at room temperature. Let's not heat this up at all, right? And in fact, we demonstrated that we can take that polyamic acid salt here in the middle, right? We take that salt, we neutralize those carboxylic acids and the polyamic acid, and we introduce cross-linkable sites, right, that are red. What does that mean? Well, it means now that we're making a foam that when it sees the radiant heat and light of the fire, that is going to be taken to our advantage. We're going to use that, right, to take these molecules and basically tie them up, make them not migratable, make them one giant molecule that ultimately will convert to carbon. Really what we're after in this approach, as we go down from, this kind of step in the middle and we introduce that red molecule, is to do everything at room temperature. So synthesis and commercial scalability wise, yeah, this is really much more feasible, right? And it's so that simple approach, right, allows us to more quickly access those larger quantities, right, of material that we want to use to, get into some real testing and some further exploration. So the other thing to demonstrate too is that we want to show that those red cross-linkable sites, those acrylates, are in fact cross-linkable. And this is possible. We're looking at the modulus of the foam, the stiffness, right? So these sulfonated polyamic acid salts, or this SPAS, right, is enabled to cross-link, right, upon heat or light. The modulus is easily measured. We have variometers that, can be imposing a light source from the bottom. We can watch the stiffness of the foam change as a function of irradiation, and we can actually, lo and behold, kind of demonstrate, right, that these polymers, these foams, will essentially increase their modulus and their stiffness. In essence, what is the mechanical properties and the microstructure of those foams, and how do those fundamental structural, elements, right, influence the performance and fire suppression? So we also did a fair amount of small-scale fire suppression. I have to use that word "we" very generously because this is in partnership with Jensen Hughes and looking at screening these foam formulations, right, using some test protocols such as, 2 gallons per minute foam applied to the classic, right, 28 kind of square foot fire, right? So we're looking at a pool fire. We're basically introducing the foam to that, kind of planar substrate, and then we're looking at suppression, extinguishment, and burn back, right? So we'll talk about how these foams are behaving under that, kind of set of criteria. So again, just for people who have not done these experiments before, I'm sure there's many people in the audience that know more about this than I do, right? But these mil-spec testing protocols, right, are kind of summarized here for us. I just spent a good week up in Minneapolis looking at a variety of these different testing protocols. But these are some standard, kind of metrics and experiments, right, that people in the field are using to kind of evaluate these next generation foams. So these foams will cross-link, and here you can see when exposed to some radiant heating, the foam is, kind of being suppressing the fire, right? You see some flamelets over on the corners, on the surfaces, the edges, but that foam is being introduced to that surface. This is a foam where the polyimide has been made at room temperature, right? Commercially viable. The acrylates are cross-linking, and we're beginning to see really nice suppression, right, of these tested foams. We also introduce alkyl surfactants together with these sulfonated polyamic acid salts, again, like we saw before. We also have some further modularity in addition to introducing those red acrylate groups, we can also introduce groups that make the polymer even more water dispersible, and we get excellent foam stabilities, right? Greater than 30 minutes of that foam, and drainage times, expansion ratios, they're exceeding the mill specification. So these are also forming quite beautiful foams. You'll notice the color of the foam, if that's important to you, right? It's much suppressed. So we've made a lot of progress in understanding how to prepare those. So we've demonstrated that mixtures actually of the water dispersible polyimide and these salts that contain these, kind of water dispersible cations, these are suppressing fire. You see the amount of foam necessary to do that, and the amount of time, again, 25 seconds to take that planar 28 square foot fire and suppress that using the foams that were just described to you. So in the last couple of minutes, as I begin to conclude, what's next? What are we doing? Well, we continue to look at the modularity of a polymeric amphiphile, a polymeric foam, as opposed to a PFAS or a PFAS type small molecule, right? We can also introduce phosphorus, right, to the sides of these groups. And it's well known, right, that phosphorus containing polymers have excellent, fire resistant and flame resistant properties. So we now continue even to further enhance, right, the performance of these polymeric, polyimides, right, these polyimide foams, right, to even increase their dispersibility, but in addition to increasing their performance in terms of suppressing of fire. So we continue to do this. We're looking at new ways to neutralize those sulfonated polyamic acids, ensure good water solubility, dispersibility, keep this synthetic process simple, right? Make it modular, and make the learnings that we come up with, also adaptable or extendable to the many other researchers who are trying to tackle this particular problem, right, in partnership with SERDP. So in the last couple of slides, just to say the future directions, we continue to look together with Brian Latimer at Virginia Tech. We continue to look at the influence of the foam itself, right? What is the foam microstructure? What's the pore size? What are the diffusion mechanisms and permeabilities, right, of these organic vapors through this complex foam structure? So thanks to SERDP for, kind of supporting these kind of fundamental questions, right? These fundamental investigations, because at the end of the day, I think this is what it's going to take, right, to really begin to kind of tackle, right, this big challenge that has been presented to us. And we've begun to do that. We can look at the design of surfactants, continuing what we discussed today. What is the modular strategy? What are the different design parameters that we can use? And how do those design parameters translate to properties and performance, right, of a foam? So we continue to do that. So let me conclude my lecture. I think I'm just about on time. And I've tried to show you a fairly promising platform for an AFFF replacement. This is I think it's a paradigm. I mean, we're using a polymeric sulfonated polymer. We can synthesize these at commercial scale. We can characterize them at the lab scale. and we can establish some of their performance using standardized testing like the mil-spec specifications, for example. We have future directions that I've described to you that we continue to look at, again, trying to put a structure property performance relationship that will guide the future directions. So my final slide, let me say, thank you to the Department of Defense and SERDP. This particular funding has led to commercially viable and modular polymeric foam platform. And I've described many of these things to you today in terms of what we think is the kind of technology readiness level, for these solutions. And also, SERDP and the DoD has established a multidisciplinary relationships. Arizona State University, which is where I'm currently located at, you can imagine fires in Phoenix are not something that we really welcome at all. And Virginia Tech, Brian Latimer, Jensen Hughes for some of our collaborations, Army Engineering Research and Development Center, the ERC in Vicksburg for some of the ecotoxicology data. I want to thank Brian explicitly. Brian's a great colleague, real expert in fire. Jensen Hughes for all the scaled up foam testing, and Clay Arrington and Ben Stovall. Now they've moved on from their graduate studies, but two really productive and passionate graduate students who helped us with this research. And thank you, Jennifer, for my time.
Wonderful. Thank you so much, Tim. I want to remind our audience at this time that you can submit questions using the Q&A box. We have a number of questions. Tim, a lot of the questions deal with toxicity and environmental fate. There's some curiosity about, kind of a new type of chemical being released to the environment. So just specifically, one question from the Illinois Environmental Protection Agency. When looking at toxicity, did you explore potential bioaccumulation magnification at all in ecosystems? Do you know if anything is known about bioaccumulation?
No, I mean, it was a little bit beyond the scope of what we are going after, but I'm very sensitive to that question because the last thing I want to do is put something on a fire that's worse than what we're starting with, right? So once we put a molecule down, yeah, it's in the ground, right? So what are we doing? It's not maybe migrating into our water, but perhaps this polymeric structure is staying in soil, right? So we have not investigated that. There's no fluorine, right, in these solutions, which I think is important, right? That carbon fluoride bond is wonderful if you don't want eggs to stick in your frying pan, or you want a chemically or oxidatively stable polymer, but it's not wonderful in the environment, as we all know. So one advantage, of course, is that we've eliminated fluorine in the entire system. And the other approach that we're looking at is hoping that the molecule basically is converted to carbon. Now, that's still an open question. So the question is a very good one, and we have not looked at, bioaccumulation. We know it's an issue. It's on our radar screen, but it's not something that we've done at this early onset, right, to address.
Okay. And one more specific question as a follow-up. There are limits to phosphates due to the concern of nutrient loading in surface water. Do you see that phosphates could be released?
Phosphates. Okay, so right now I don't imagine a mechanism for that. We're not putting kind of phosphorus into our first generation product. I suppose if we have phosphorus in some of the phosphonium containing cations that I talked about for future directions, that there could be avenues or mechanisms to produce a phosphate. But all the efforts so far have not involved any phosphorus containing, right, molecules of any kind, right? So I don't think that's an issue, at least in our first generation product, but the question's good because it kind of raises a, kind of a concern, or maybe say a consideration, right, as we begin to think about phosphorus in some kind of fire suppression foam. Yeah.
Great. All right, so now we'll go to the chemistry. When adding the acrylates, is there a loss of the full aromaticity? And does that impact temperature stability and charring characteristics? Or is the aromaticity maintained?
Yeah, so the aromaticity is maintained. I mean, one of the nice things about the aromatic ring is it's stable. And from an environmental standpoint, one of the bad things about aromatic rings is that they're stable, right? But they are not reactive. So the aromatic rings do not hydrogenate or react in any way. They stay completely aromatized, right? And ultimately what we hope is that during the fire process itself, that they convert completely to a fully sp² hybridized carbon, right? A graphene of some kind, right? So they're not going to open up or do any chemistry like that. They stay intact. Yeah.
Okay, great. And then we have some questions about what kind of fires this might apply to. Do you have any idea of these chemical formulations would work on like mineral oil fires, for example, or would that be different?
Wow, that's an interesting question. We have focused on, because of our attention from SERDP and DoD, on hydrocarbon-based fires. We have not looked at like a mineral oil. So we have not evaluated that. So I don't know if I can answer. Of course, as an optimist, I'm going to say, yeah, it's going to suppress that fire. But I think the question you're getting at, is what is the role of that hydrocarbon or that fuel source, right, transporting through the foam structure? And I think that's an opportunity that sort of continues to try to address through some of the funded programs, right? How do we understand how those molecules, how did a mineral oil diffuse through the foam versus, say, a hydrocarbon, right, or some type of other, kind of more hydrocarbon-based fuel? So we haven't tested that, but I think you're right that that's going to be an issue, and how not all molecules are created equal, and how they diffuse through the foam, and how the foam structure influences that diffusion, I think is an important fundamental question to address. A good question.
Okay, great. And are there monomers that are available for the polyamide manufacture?
Yes, there is a vast library of dianhydrides, and we're looking at all of those. There's a lot of reasons to pick certain dianhydrides that are basic to the United States, right? Looking at just kind of regional resiliency of some of these starting feedstocks, that's an important question, of course, right? So the answer is yeah, there's a lot of variability that we can look at. We could also even look at an oligomeric species. Say we want to introduce siloxanes, right, for example, to the polyimide, very easily accomplished, right, with the introduction of an amino-terminated siloxane. So not only are there small molecules available to us that we can begin to construct these new molecules, new foam, but we can also think about oligomeric species and think about kind of some of the advantages of silicon-containing polymers in these solutions.
Great, and we have one last question for you, Tim, before we bring back Terry and Joe. Have you done any assessment of what the shelf life of what it might be, or any aging studies?
Yeah, so we have done that, and that is important because ultimately this polymer needs to sit in solution on a fire truck somewhere or in a drum somewhere for a period of time. So once we neutralize the polyamic acids or the intermediate, right, and we look at their stability in water, they're fine. Right? We have not seen any hydrolysis or degradation of that polymer if they're fully neutralized, and that's what I described to you today. So the answer to that question is that yes, these are stable in an aqueous environment. Polyimides themselves, right, are rock solid, right? They are going to disperse in water, and there's nothing that water molecule or temperatures, typical temperatures, are going to see, if they're going to see, are going to influence that. So another reason for choosing the polyimide structure was to address that very question, right? That there's no hydrolysis mechanisms or degradation in water at typical storage temperatures for these types of products.
Okay, great. Thank you, Tim.
Yeah.
And at this time, we'll bring back Joe and Terry. And we have a few last questions they're actually very good questions. The first, Joe, is for you. Can you comment on whether the treatment technology that was described could be expected to meet increasingly lower PFAS standards, such as 10 nanograms per liter?
That's a great question. You know, the work we've been doing has been looking at the standards that we're considering today. But the pretty exciting thing about the SPEC performance so far is that it's a lot more effective mass per mass than GAC. So we think, you know, the performance in terms of specific sorbents is going to slide a little bit to the left, but similarly, performance metrics for GAC and other resins are going to slide to the left on Terry's graphs. Terry, did you have anything you wanted to add to that?
No, I think that's a good response. Also, in terms of how we approach these very low levels, we may look at how we arrange the system. Instead of a single pass, we may have, you know, two passes, operate them in series, or tie them in with other technologies as well, in order to get from these very high levels to single-digit type effluent levels.
Okay, great, thank you. Tim, this question for you is from the U.S. Army Corps of Engineers. Would this polymer-based technology compound work effectively with the current delivery systems for AFFF that are currently in use? Can the same equipment for delivery be used?
Now, that's a really important consideration. Thanks for asking it. We have not tested it, you know, in real life equipment. My sense is that these polymers are operating at the same concentration and viscosity, right, that is currently being used in the current, you know, equipment. So my sense is that, you know, they're going to flow and move without any difficulties. Also, they're not corrosive in any way, right? They're not going to corrode or do anything, I think, to the, you know, the actual structure of that delivery system. The answer is, you know, I don't know exactly, but I can't imagine any types of situations where it would precipitate or become too thick or become too unstable, or maybe, you know, somehow affect the surface, you know, that they see. I think they're going to be stable, although we have not tested that.
Okay, great, thank you. Direct this next question to Terry first. What applications in industry might the treatment system be a good fit for? For example, could it have a small enough footprint that it could be integrated into a naval vessel with respect to cleaning AFFF effluent?
Yeah, of course, that's another good question. I would say, you know, what the technology is suited for, you know, higher levels of PFAS. If it was for example, groundwater, a drinking water application with low concentrations, that might not be a good application. But on a naval vessel, you know, as we've shown with the lab scale unit, it's scalable to very small levels as well. Our benchtop unit, which is you know, literally sitting on top of a table, can treat upwards of you know, 200 liters per day. So the technology is scalable, and depending on the waste characteristics, it might be a good you know, option for that type of application.
Great. Tim, are the polyamide compositions suitable for scale up and partnership? And who would be the key partners moving forward?
So Jennifer, can you repeat that? Was it, you say commercial partners?
Are the compositions suitable for scale up, and who would be the partners in that? Who would need to be involved?
Yes, I mean, that was a consideration that we, you know, had really, even though we're looking at fundamental research in our project, you know, still, you know, that was a consideration for us. So these are scalable. I mean, there's a variety of companies, you know, across the United States that can, you know, take a dianhydride and a diamine, right, and make those at room temperature. Many companies across the U.S. There's obviously big players, you know, like DuPont or Sabic, which are located in the United States. But there's also many small companies that are manufacturing polyamides regularly. So I believe that this process is scalable. I think it's energy efficient, and I think that it is a relatively easy kind of process to, you know, to scale.
Great, that was an excellent wrap up. Thank you, Tim.
Mm-hmm.
And then as we wrap up, Joe, would you please summarize the next steps ahead for the treatment system?
So like Terry mentioned, right now we're starting to run the system with 2 reactors in series, so we can see how low we can go and how that impacts, the performance of the system. More and more we're seeing folks line up GAC and resin or treatment trains, and there's some advantages with SPAC having less susceptibility to some of the issues that make it difficult for resins, like ions in the water, for example. So really, that's part of it, is to see how low we can go. And then the next end of it is Terry and the team are working to evaluate how reliable the bench testing can be, so we can use it as a better, reliable way to pre-design systems and kind of short circuit the process. One of the big advantages of GAC is it's readily available, easy to implement, easy to design. It's a little more complicated to do things with resin. We think that this approach for the SPAC CMS system is going to allow us to dial it in and bridge that gap a little bit better. So that's what we're hoping to accomplish.
Great. Thank you, Joe, and thanks to Terry and Tim as well. We appreciate the presentations and all of the very good answers to the questions today. And in this series, our next webinar is on Thursday, October 7th, and it will discuss adapting to changes in the hydrologic cycle under variable climate conditions. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you want to refer to them in the future. And we would appreciate it if you could please take a moment at this time to complete the survey that will pop up on your screen. And this concludes today's webcast. Thank you.